Hi, my name is Aaron Sampson. Computers are immensely useful tools that continue to change the world we live in. Arguably, they would be far less useful without the ability for them to communicate with each other using networks. In this course, I'll cover concepts surrounding networking and wireless technologies, beginning with the basics of networking and the common protocols we use every day for browsing the internet and sending email. Then I'll introduce networking devices and firewalls and finish up with the characteristics of wireless communications, including wireless quality and best practices. Upon completion, you'll have built the foundation for the basics of IT. This course helps to prepare learners for the CompTIA IT Fundamentals or ITF Plus certification exam FC0 U61. In this presentation, we'll provide an overview of the basics of networking communication, which at its core really comes down to the use of protocols. Now, these are just rules that are defined so that any two entities that are communicating can do so effectively. And really, if you think about just something like a conversation, we always have rules that we follow so that the conversation can be understood. In other words, it defines the mechanism by which communication can occur. And one of the nice things about protocols is that they are hardware and or operating system agnostic. In other words, it does not matter if I'm using something like a Windows PC and you're using a Mac. Our systems can still communicate with each other if the right protocols are in place. Now, we'll talk more about some specific protocols a little bit later on, but ultimately, as long as every system follows the same rules, then they can communicate with each other in a networked environment. Now, with respect to that networked environment, there are effectively two components of any given network: the physical network itself and the logical network. Now, the physical quite literally refers to the layout, the devices that are in use, and the manner by which they are connected with each other, for example, using network cables. The logical network, however, refers to the software and or the applications that are being used and the types of protocols. So you can have a different kind of logical network layout on the same physical network by simply changing the protocols or changing the applications. So when you're designing something like the physical network, you are actually concerned with the physical placement of devices and how they're connected. But again, different types of logical networks could be implemented on the same physical infrastructure. Now, in terms of the components of a network, it really comes down to the nodes themselves, which do refer to the actual devices that are communicating on any given network. So even something like your home environment, as an example, if you have a laptop computer, maybe several smartphones and or tablets, and possibly even something like a gaming device in your home, then each one of those is a node and they can all communicate with each other. And that communication is facilitated by a process known as switching. Now, we'll talk about this in greater detail a little bit later on as well, but switching refers to the fact that the communications overall are broken down into smaller units known as packets, and any given packet represents a portion of the overall communication, and they're sent among all participating nodes to facilitate the overall communication. Now, with respect to all networking, there is a model that is in place known as the OSI networking model, and that stands for Open Systems Interconnect. And this was defined largely to ensure that all networking components can be developed so that they're compatible with each other. Now, there's nothing in any interface that you and I will ever use that indicates these layers, and even as a developer, there's nothing that you have to do that specifically states I'm developing something for the session layer or the network layer. It's simply a structure that is followed by anyone that is developing anything to do with networking. Now, a good way to envision how these layers work is to think about a process such as sending an email. And just as a quick introduction, I'll focus on the two extreme layers. So if I'm composing an email, then I'm at the top, the application layer. I'm using an email application to compose a message. But ultimately, when I send that message, it has to cross something such as the physical wires of my network. So that's the physical layer. So how do I get from typing in words and phrases into an email application down to literally sending electrical signals on a physical wire? That's the overall process that happens in all the other layers. So again, imagining that email situation, once I compose my message and I hit send, then the information that I just composed begins to get packaged up, if you will, and it travels down the stack until it gets to the physical layer, the actual wire of the network. It would then traverse the network, and let's say I sent that message to you and you were on the same network. It would be received at the physical layer of your system, and that information would then travel up the stack until you view that information in your email application. So again, just looking at the extreme layers, I used an application to convert information down to physical electrical signals that traveled across a wire. Those signals were then received by your system. They traveled up, and you see the same information that I typed, but in your application. So again, all of those layers in between will process and add more information to what I composed so that the network protocols that are in place can effectively transmit that information and be received on the other side so that you effectively see what I sent. Now, in a little more detail, the application layer does define the software that I'm using to a degree, but more so it would define the protocols that the applications use to begin processing this data. So again, using something like an email application as an example, those types of programs use specific protocols amongst each other to ensure that we can communicate with each other, and email applications use a protocol known as SMTP, which stands for Simple Mail Transfer Protocol. So that would be an example of an application layer protocol. Now, we'll talk about that in greater detail later on, but there are other types of applications, of course, that are used in any networking environment, and each one would have its specific protocol so that the receiving computer understands what information was sent in the first place. The presentation layer would accept the message that I just sent, and if appropriate, it would do something to it to ensure that it is again understandable by the other side. Now, two very common examples of processes that occur at the presentation layer are compression and encryption. So if, for example, I was sending a secured email, then my presentation layer is responsible for encrypting that information. When you receive the email, your presentation layer is responsible for decrypting that information and presenting it to the application layer in a readable format. Now, I never see anything with respect to applying the encryption, and you never see anything with respect to removing the encryption. It's all handled within the presentation layer. The same thing would apply to compression. The presentation layer would compress the data on my end, but it would decompress it on your end. The session layer is responsible for maintaining the connections between the two systems, so that, again, as soon as I hit send, a session is established to your computer as the recipient, and it makes sure that the session remains intact until all information has been sent and received. And you can think of that much like a phone call. We make sure that we don't hang up on each other in the middle of a sentence. So we ensure that all information has been exchanged before we close the session or hang up our phones. The transport layer is responsible for determining what type of transmission is sent. Now, I realize that's a little bit of a vague statement, but for this, I want you to imagine something like sending an actual package with a courier. There are two primary protocols at the transport layer. One is called TCP, Transport Control Protocol, and one is called UDP, which is the User Datagram Protocol. TCP guarantees communications. UDP does not. So again, coming back to sending a package with a courier, you can just go to the courier, hand them this package, and say, send it. It might get there, probably will, in fact, but if you want to, you can ensure it or you can guarantee its delivery by requiring a signature from the recipient. So TCP is that guaranteed communication. UDP is just sort of a best effort, if you will. If a packet happens to get lost during transmission, if TCP was used, that packet is retransmitted. If UDP was used, that packet is not retransmitted and you'd have to try all over again. Okay? Now, that begs the question, why would you ever use UDP if it's not guaranteed? Well, the answer is that it's faster. It certainly is safer to use TCP. You know that communications are guaranteed. But the way that packets are guaranteed is that the sending system requests an acknowledgement of the receiving system that the packet was received, very much like the signature on the physical package sent through the courier. So ultimately, TCP is safer, but it's slower. UDP is less reliable, but it's faster. The network layer defines the physical path that data will take as it's being routed throughout the network. So it quite literally is, how do I get from point A to point B? You can imagine that as using something like a GPS to find the actual pathway. And the data link layer defines the format of data on the network. For example, what type of packet has to be formulated? Is it a physical Ethernet network or is it a wireless network? There are different formats in use for each type of network. Then finally, down at the physical layer, this is where the data is converted into the appropriate electrical impulses to traverse that particular type of network. So again, that's the overall process of communication. But as a user, all I see is an application in front of me. Everything else happens in the background, so to speak, and the same applies for you. But as a developer, if I want to start creating anything to do with networking, then I basically choose a section of this model. If I'm developing new software, well, that's the application layer, and it might dabble a little bit into the presentation layer, if you will. But if I decide that I want to manufacture network cards, well, that's down at the physical layer. If I'm developing new protocols, those might fall anywhere in between the session layer and the data link layer, again, depending on the type of protocol that you want to create, but they all just define rules so that ultimately applications can make use of physical networks with all of the necessary processes in between occurring in the background, so that regardless of which applications I'm using or even what type of network I'm on, if the correct protocols are in place, all devices can communicate with each other in a compatible and reliable manner. In this presentation, we'll examine the role and features of the Internet Protocol Suite, or what you and I generally refer to as TCP/IP. But while TCP/IP is not owned by anyone, its development did begin in the United States Department of Defense in a branch referred to as DARPA, which stands for Defense Advanced Research Projects Agency. And as such, you might hear this sometimes referred to as the DoD model, or Department of Defense. But since then, it has certainly become a global networking standard. But the primary characteristic of the original model was to define a protocol stack, meaning that there are several protocols within the overall protocol, if you will, and it's referred to as a stack because any given protocol will perform its job and pass it off to the next, if you will, in a layered structure. So overall, the Internet Protocol Suite is used for effectively any type of client-server model whereby you have a client system that makes a request of a server and then the server satisfies that request. So any two systems that are using TCP/IP can communicate in such a manner. It does not matter what the operating system is, and it defines the start-to-finish data handling process. In other words, it ensures that all requests are fully satisfied. And as mentioned, the stack nature refers to the fact that there are multiple layers of the suite overall, each layer containing multiple individual protocols, but they all work together to complete any particular task. So the top layer is referred to as the application layer, and this does refer to the software that you and I use, but more specifically, It's the protocols in use by that particular software that matters. Now, there are a lot of examples here, and we don't really have time to go through every single one of them. But common and very likely familiar examples would include something like HTTP. You have likely seen this every time you've opened up a browser. So that simply means that the application of a browser uses that particular protocol to ensure that it can present you with the appropriate information. So we open up our browsers and we enter in a website, but it's the hypertext transfer protocol that defines the specifics of any given request. This is so that the server on the other end, satisfying our request, knows what is being asked of it, because that server can probably perform any number of tasks. But when it receives a request over the HTTP protocol, it knows that we are asking for its website. Similarly, if we jump all the way to the third column, at the top we see SMTP. That's the Simple Mail Transfer Protocol. So again, any given server can perform any number of services. But when it receives a request from the SMTP protocol, it knows that we are attempting to send email. So again, the application from our perspective would be something like an email client, but the server sees that protocol and realizes that we are attempting to send and or receive email. Other examples here include DHCP, which is the Dynamic Host Configuration Protocol, which is responsible for assigning IP addresses to client systems, and DNS is the Domain Name System, which is responsible for resolving a name, such as www.myfavoritewebsite.com, to an IP address, so that TCP/IP can use the address, but we can use a simple and easy to remember name. Now again, there are a lot of other examples here. We will discuss some of them in greater detail as we move through the course here. But again, the general idea is to simply ensure that any given application identifies the type of service that is being requested of any given server. The transport layer protocols include the datagram congestion control protocol, the resource reservation protocol, the stream control protocol, but much more commonly, the core protocols used in the transport layer are TCP, the Transmission Control Protocol, and UDP, the User Datagram Protocol. And they define how packets are sent. Now, in that context, it refers to whether the packets are guaranteed to be delivered or not. TCP is guaranteed delivery, and it uses acknowledgments. So if I send you a packet, I request an acknowledgement that you received that packet before I send another one. So that results in very reliable communications. Something like email does use TCP. UDP, however, is not guaranteed. It does not use any acknowledgments, so that sort of begs the question as to why you might use it. Well, the answer is that it's fast. If you are streaming a video, for example, you want speed. So UDP is preferable in that scenario. If you are streaming a video, if a packet is lost, it's not a big deal. You might see the screen blip a little bit, but it's not critical. But if you're sending an email and packets are lost, then that could be critical, so the packets are retransmitted when TCP is being used. But again, that takes time. The acknowledgments slow things down. Ultimately, TCP is reliable but slow. UDP is less reliable but fast. And then at the internet layer, we see protocols including the Internet Control Message Protocol, which has two versions. It's original and version 6, which comes down to the IP version 4 and version 6 that we see below, but I'll get back to that in just a moment. IGMP is the Internet Group Management Protocol. Then IP is simply Internet Protocol, which, as mentioned, comes in two versions, versions 4 and version 6. Now, we'll actually compare those two in an upcoming demonstration, but for the time being, it's certainly safe to say that version 4 is very heavily used still, although version 6 is the newer and more efficient implementation. Again, we'll talk about both of those in much greater detail a little bit later on. And IPsec is to secure IP. But ultimately, the IP protocol itself is used for routing purposes to determine the best route to take, and it's also responsible for fragmenting packets so that if any given packet is too large, it will break it down into smaller, more manageable units to ensure that communicating systems don't overwhelm each other. And finally, the data link layer protocols is the lowest layer, and it defines the format or the structure of the packets themselves depending on the type of network that is being used. Now, again, there are more examples here than we can cover in a short presentation, but for example, Ethernet versus FDDI refers to two completely different methods of networking. Ethernet is probably what most of us are familiar with, but FDDI is the Fiber Distributed Data Interface in use for fiber optic networks. So again, those are two completely different methods of networking. So this defines the actual format and the structure of the packets for those particular types of networks. Now, there are clearly other examples here, and certain protocols do not really have to do with the type of network, but they refer to the final stage of the protocol processing before the packets are submitted to the physical media itself, such as the network interface and/or the wire being used. So ultimately, as mentioned, all layers work together so that when I'm working in an application, I can formulate whatever request it is I want of the server on the other side, or even just another client, but someone is responding to my request. So from that point, it goes through all of the appropriate protocols in all layers to make sure that a packet is constructed that is appropriate to the type of network that I'm using and/or the type of request that I submit. And all protocols of all layers provide us with the ability to communicate in virtually any situation with any application and most likely any type of operating system. Ultimately, as long as the two communicating entities are both using TCP/IP, then the complete suite of protocols within TCP/IP will allow us to communicate under any circumstances. In this presentation, we'll provide an overview of the basic role and features of TCP/IP, which is a networking protocol that is typically installed on all network clients and all servers to facilitate the client-server model. Now, just quickly in that regard, while we tend to think of client systems as regular desktops and laptops or even mobile devices, and servers as the big systems that sit in some back room somewhere, that doesn't really have to be the case. In essence, any two systems that are communicating with each other will always submit requests of each other, and they'll always respond to those requests. So if, for example, you're in a fairly small network, such as the home environment or a small office, you might make a request of another client system in that environment, such as if there's a shared printer. So even though there's no dedicated server, there is still a system that responds to those print requests. So in that regard, it is acting in a server capacity. Now, by and large, clients and servers are exactly what we think of, but ultimately any system can be a client as long as it is making a request of another system. Then it is a client. And any system can respond to a request, in which case it's a server. But that aside, TCP/IP has certainly become the most common protocol by far in client-server networks. And as a protocol, it's not just a singular protocol. And in fact, even in the name, TCP/IP, there are two protocols listed. But there are actually many protocols in the overall suite that are divided up into layers. Now, we'll take a look at those layers in just a moment, but they each serve different purposes to ultimately ensure that the correct type of packet is created to send over the network for the appropriate type of service. Now, as for the protocol itself, it's a non-proprietary protocol, which means it's not owned by anyone. It had its roots in the U.S. Department of Defense, but ultimately it's developed by consortiums and various groups. So again, no one owns it, which makes it very compatible. Almost any system in use these days can support TCP/IP. And as such, it requires minimal maintenance and is very reliable. It has been in use for a very long time, and in terms of most client systems, nothing has to be done other than to possibly enable it. It might be an option that you could turn off or disable on a system, but you'll almost never have to actually install it. It's almost always present in all systems by default. So again, chances are you don't need to do anything to start using TCP/IP. Now, as for the key elements, as mentioned, there are in fact multiple protocols, and as also mentioned, two of them are listed in the name, TCP and IP. Now, despite the fact that there are in fact many more protocols, these are sort of the core protocols, if you will. TCP is the Transmission Control Protocol, and IP simply stands for Internet Protocol. TCP is responsible for a particular type of delivery that is known as guaranteed or acknowledged or simply just reliable communications. When any system sends out a packet to any other system, if TCP is being used, then it will request an acknowledgement of receipt of that packet before additional packets are sent. In other words, I know that you have received what I just sent, therefore I will send more. If I do not receive the acknowledgement, I will assume that the packet failed and I'll retransmit it. So that results in very reliable packet delivery. IP is effectively responsible for determining the correct route to take and possibly fragmenting larger packets into smaller units for greater flow control. Now, another component that is required in all TCP/IP communications is what's known as a subnet mask, and this determines the overall size of any given network and or when any given system will have to communicate its default gateway, which I'll come to in a moment, in order to reach the intended recipient. Now, any two systems that are on the same network within the same subnet will be able to communicate with each other by default without needing any processing. But the IP address, in conjunction with the subnet mask, will determine if any two hosts are in fact in the same network. And as mentioned, if they are, then that's it. They'll be able to communicate. But if they aren't, then what you need to do is contact your default gateway, which gives you access to other networks. Now that comes down to the final component, which is the default gateway. Now I should point out that a gateway is actually not required just for TCP/IP to be able to work, but if you do not have a default gateway, then communications are limited to within your own subnet only. So if you need to get to another network, then this is where the subnet mask figures that out, for lack of a better word, and when it determines that the destination is on another network, it will simply forward the packet to the default gateway, and then that's it as far as it's concerned. It's now up to the gateway to find the next network and ultimately locate the host that I'm trying to reach. So again, a default gateway would not be required if you were only within a single network, but almost all of us are in environments where we need to communicate with other networks, most notably the internet. So without a default gateway, you would not be able to access the internet or any other network. Coming back to the layers of TCP/IP, there are four: the application layer, the transport layer, the network layer, and the physical layer. And this is sometimes referred to as the data link layer. But each layer has its own specific job, if you will. The application layer defines the type of service or application that is being used. One very common example would be using a browser. When we open up a browser, we see HTTP in many cases, which stands for Hypertext Transfer Protocol. So that's a sub-protocol, if you will, of the entire suite, and it defines the type of communication that is being requested of the server, so that when the server sees a request coming in over HTTP, it understands that it's the website that is being requested of that server, because that specific server can likely perform any number of services, but the application layer protocols define exactly which applications we are wanting to use. Similarly, if you are using email, then the application layer protocol would be something like SMTP, or Simple Mail Transfer Protocol, which again identifies to the server that this is what's being requested of it. It wants it to process email. The transport layer is responsible for that type of communication that I just referred to with respect to TCP. TCP resides at the transport layer and provides those guaranteed or acknowledged communications. But there is another protocol at this layer known as UDP, which is the User Datagram Protocol. And it does not use those guaranteed or acknowledged communications. It just sends everything out. Now, you might ask, well, why would we not want to use guaranteed communications? Well, it simply comes down to speed. Sending a packet out and requesting an acknowledgement, then sending more packets and requesting more acknowledgements takes time. If you just send, then it's a lot faster. Something like email does use guaranteed communications because we don't want to lose packets. But something like streaming a video does not use guaranteed packets because we want speed. The network layer is responsible for routing and determining the appropriate network boundaries. So again, this is where we see IP. And finally, the physical layer uses its protocols to formulate the correct type of packet to place onto the physical media, such as a wired Ethernet adapter versus a wireless communication. Each one will use different formats for their packets. So as for the importance of TCP/IP, again, the fact that it is not owned by anyone makes it very easily modified and very easy to implement in any environment. And due to the nature of its development, it is extremely scalable. You can, in theory, support an unlimited number of devices with TCP/IP. Now, I'll qualify that statement by saying you would need to be using version 6 of the protocol, but with the correct implementation, you can still even use version 4 with very large networks, provided they are internal networks and not directly connected to the internet. But ultimately, any environment can implement TCP/IP, and all devices within that environment would support its use. In this video, we'll outline the basic features of network packets, which in short represent the units of data that are transferred between any sender and receiver. Now, this is the basic process that occurs within any packet-switched network. And the term switching goes all the way back to the days of telephones, whereby to complete a circuit, an operator quite literally used a cable to connect from one end into another to complete the circuit between the two phones attempting to communicate. But then, of course, when that call was ended, you could switch it to any other connection for the next call. But that is basically what happens in networking today. When I want to send you information, the devices that connect us create circuits within them so that I have a physical pathway between us so that we can exchange information. The packets are simply the units that we send. So why bother using packets? Well, data simply needs to be broken down into more manageable pieces to facilitate more efficient transmission. Now, just as a more realistic or real-world example of this, if you imagine yourself speaking on the phone with someone and you are trying to, let's say, register for something, they will require things like your name, your address, your phone number, and various other types of information. And in almost every case, you'll just give them one piece of information at a time, such as your name, then your address, then your phone number, then your email address. If you tried to give them all of that information in one shot, they would almost always ask you to repeat something. Now, when it comes to computers, it's not that the computer couldn't understand that much information. It really just comes down to consistency. If packets are more or less the same size, then it just becomes easier and more efficient for all of the devices involved to process each packet. Whereas if every packet was a widely varying size, it would simply be less efficient. And if you think of something like an assembly line as another example, those are far more efficient because everyone has a very dedicated and specific task that they repeat over and over again. So the overall efficiency simply increases by using packets. As for the components of a packet, each one includes a header, a payload, and a trailer. The header will typically include information such as the destination address and the source address that sent it. The payload represents the data itself, and the trailer usually includes some type of error correction mechanism. Now, to put that into a more day-to-day context, if you were to send a letter, on the outside of the envelope, you would write the destination address, and you might also include your own address so that if it fails to reach its destination, it can be returned. The payload would be the letter itself, or whatever the contents are, and the trailer or the error correction code might be something like insuring the letter or registering it with the post office so that you have some way to track it. Now, that's not an exact analogy by any means, but it gives you a general idea as to how there are varying components to something like sending a letter. It's not just a matter of writing a letter and dropping just the letter itself into the mailbox. More information needs to be supplied in order for the communication to succeed. As for the transmission of the packets themselves, routers are actually the components that are responsible for determining their path. Now, we of course have to indicate where the packet is destined, but it's not up to our systems to determine how to get to that destination. That's what routers do. But it's not always guaranteed that the router will always find the best path at any given time, and I'll come back to that point in just a moment. Or there could be problems with the transmission. So packets can actually be rerouted to use different paths or retransmitted if there is an error. And that comes back to that error correction code that I mentioned a moment ago. If there is any type of failure, it will actually try again to make sure that it can be delivered. And finally, some other advantages include the fact that packets can be encrypted. So if we need to send secure information, encryption can be applied so that if packets are intercepted, they're in an unreadable format to anyone other than the intended recipient. And as mentioned, routers are responsible for making the choice in terms of how to get the packets from point A to point B. And any given router will always attempt to use the best available route. But the key word there is available. There are almost always multiple different pathways to get from point A to point B. Now, that's dependent on the situation. If you are in a smaller environment and you only have one router that separates network 1 from network 2, then there is only one path. But in terms of the internet, there can be any number of paths available. So packets can in fact be routed to different paths, even if they are all part of the same communication. But packets are numbered and sequenced so that ultimately when they arrive at the destination, even if they arrive out of sequence, they can be reassembled into the correct sequence. So again, it's possible that during transmission, one packet might take route A because at that particular moment, that is the best available route. But something could happen so that by the time later packets arrive, that particular route might not be the best available route. There might be another option that's less busy. So there are situations where packets are routed along different paths. And also mentioned earlier, there can be error correction code to ensure that if there is a problem, the packets can be retransmitted to ensure that they arrive intact at their destination. So again, it's simply a matter of taking the overall communication that needs to happen and breaking it down into smaller units. This allows for greater efficiency, greater speed, and ultimately more reliable data transmissions. In this presentation, we'll identify the basic features of the Domain Name System, or DNS, which is a service that can be thought of as the directory for the internet with respect to how we as users are able to establish connections to the servers that host the websites and services that we want to access. Now, the key to this service is the name aspect, in that when we bring up a website in our browsers, we see a domain name in the address bar such as www.myfavoritewebsite.com. And we're able to enter something like that name because DNS servers are able to translate names to IP addresses. While our browsers and other applications can certainly make use of names, and because they're easier for us as humans to remember, the TCP/IP protocol requires an IP address, not a name. So ultimately, it's the job of DNS to accept something like www.myfavoritewebsite.com and to equate that to an IP address that can be used to establish communications with that server. To accomplish that, DNS servers maintain databases that contain records that match up domain names with their respective IP addresses. Now, these examples are, of course, just made up, but they would include a name such as www.easynomadtravel.com and its associated IP addresses, both in IP versions 4 and 6 to ensure compatibility. Now, while it's not overly obvious, the fact that this name and others like it have multiple parts separated by periods is a key aspect of DNS, because it would be impossible for any single DNS server to contain every record of every name and every IP address that is available on the internet today. So the overall structure of DNS is referred to as a distributed database, whereby any given server only contains a portion of the entire DNS namespace. And that namespace is also organized as a hierarchy so that there is always a specific pathway to follow in order to successfully locate any given record. In this example, .com is the least specific portion of the name, as of course there are many sites that end with .com. But there are many other extensions as well, including .org, .edu, .net, and many that represent countries or regions, such as .ca, .us, and .eu. So various collections of servers are used to host the records of those portions of the namespace, which are also known as top-level domains. But within the .com portion of the namespace, there would be a registered entry for Easy Nomad Travel. Now, if I'm the administrator responsible for maintaining the internet presence for that organization, then it's up to me to register that name with a public internet registration authority, which ensures that no one else can use that name, much like registering a business name. Provided the name I want to use is available, then I must also provide the IP address of a DNS server that is responsible for resolving all names that end with easynomadtravel.com. And the DNS server information that I provide is then entered as the authoritative server for that domain, which ensures that no one else can just stand up a DNS server on their own and claim to be the DNS server for that name. But there might be several other servers within my environment that also have an internet presence. So the final component, www, indicates the particular server that hosts our website. Other servers that might be available could include mail.easynomadtravel.com or ftp.easynomadtravel.com, but each one of those would be a different server from the web server, and they would provide different services. In short, it's up to me to decide which names and which IP addresses to use within my own organization. But of course, I have no naming control outside of my organization. But again, the point is that there are portions to the name that all correspond to the hierarchical structure of the DNS namespace overall. So how does that all translate into someone in the general public being able to locate my website? Well, for starters, it comes down to the types of queries that can be issued and the types of responses that can be generated. A recursive query means that a client must either receive the requested resource record or an error indicating that the record could not be located. In perhaps simpler terms, a recursive query requires an immediate answer of either "here you go" or "I can't answer that." Now, I'll clarify that in greater detail in just a moment. A non-recursive query also expects an immediate response, but it does not provide for an "I don't know" response. Non-recursive queries will always return an answer, either because the queried server is the authoritative server for that domain, or the resource record exists in a memory cache of the server because it already looked up that same record from a previous request, in which case it will simply remember it, so to speak, for a certain amount of time to speed up subsequent requests. Now, coming back to clarifying the "I can't answer that" response mentioned a moment ago, the iterative query can be thought of as a response that kind of does say "I don't know," but more specifically, think of it as saying "I don't know, but hold on a moment and I'll find out." So that process comes back to the hierarchical nature of the namespace of the internet, whereby the names are broken down into more manageable sections. So when it comes to locating any given name, the components involved with the process include a DNS resolver, also sometimes referred to as the DNS recursor, because it is the system that ultimately finds the requested IP address for us, root name servers, top-level domain name servers, and authoritative name servers. So the entire process looks like this. When you open up a browser and type in www.easynomadtravel.com into the address bar, your system will immediately send that name to the DNS server configured as your primary DNS server in your IP address configuration, or again, what is also referred to as the DNS resolver. Now, we as users almost never have to enter that value ourselves. In corporate environments, our network administrators configure it so that we receive that value automatically. And at home, our routers from the internet service providers have them pre-programmed in. But in either case, the request goes to what can be thought of as your DNS server. But if your DNS server has never heard of that name before, then rather than just saying "I don't know" and terminating the process, it begins an iterative process to find out. Since it was handed a full name of www.easynomadtravel.com, it can break it down by first querying the root DNS servers, values for which are pre-programmed into DNS servers as soon as the service is installed. These give DNS servers a place to start. Root servers have had the same hard-coded IP addresses for a very long time and are managed by various regulated entities to ensure consistency. But while the root servers will not be able to locate the specific web server we want, one of the root servers will direct your DNS server to the .com or the top-level domain portion of the namespace. Now, there are millions of entries within the .com portion, but one of the .com servers will have a publicly registered entry for easynomadtravel.com. So that .com server will direct us to the authoritative server for that domain. With that information in hand, the resolver will ask the authoritative server for the IP address of its web server, as designated by the www resource record. The authoritative server will search its own database, discover that record, and return the address to your DNS server, who will in turn pass it along to the client, and the web page appears. Now, with respect to the query types just mentioned, all three are in play here. The initial request from the client computer to the DNS server is recursive, in that it says, "I expect an answer," but that answer simply doesn't come right away. The DNS server then issues iterative queries through multiple servers until it locates the authoritative server. Since that server is authoritative, it can issue a non-recursive response because the requested record was in its own database. Once our server has the requested IP address, it does reply back to the client with an answer. So from the client's perspective, it did provide us with an answer. So again, that's the recursive query. I got my answer. So we as clients never have to specify which type of query we want to issue. They're all issued automatically in the appropriate situation. Finally, another beneficial step of the overall process is caching, which means that once a name is resolved to an IP address, both the server that resolved it and the client that requested it will cache the result locally so that if the same address is requested again, none of that iterative process has to occur. The server will cache it for the benefit of all clients that might request the same address, and the client will cache it both at the operating system level for the benefit of other applications that might need it, and at the browser level, so that if the same site is pulled up again, it doesn't even have to look in the operating system cache. It's retained right in the browser. Now, the length of time that any given value will remain in any given cache will vary depending on several factors, but in general, cached values aren't kept overly long, in some cases maybe only a few minutes. And that's done intentionally to ensure that your caches don't just continue to grow and grow, taking up more and more space in memory. But ultimately, even the entire iterative process can usually be completed within maybe 5 to 10 seconds at worst. So even if values aren't in any caches, you likely won't have to wait for very long. While almost all of this occurs behind the scenes, without DNS, we'd all have to know the IP addresses for every site we want to reach. So DNS is one of the most critical network services in use these days. In this video, we'll provide an overview of local area networks, or LANs, and wide area networks, or WANs, along with some of their other related implementations. Now, perhaps the most distinguishing characteristic is their size. LANs are primarily used to connect systems in the same locale, such as an office, a school, or even at home, whereas WANs are used to connect systems over much wider areas, such as cities, states or provinces, or even countries. But size certainly isn't the only thing that distinguishes them, so looking at some of the specific characteristics of each, LANs tend to have higher security because you have complete control over their implementation and configuration, and the infrastructure used to create your LAN is not being shared by anyone outside of your organization. LANs also tend to be much faster than WANs, primarily due to the much shorter distances being traversed and a much simpler physical layout. For example, you might not have to route packets from one network to another at all within a LAN environment, and in smaller LANs, all systems might have direct connections to all other systems simply by being connected into the same switches, which don't require any routing at all. LANs offer many benefits, including application sharing, resource sharing such as printers and file sharing, fast messaging services including both email and instant messaging applications. All users can share a single internet connection, and everything can be managed in a centralized manner by your network administrators. Some disadvantages can include the cost, although it's worth qualifying that statement by saying this would generally only be for implementing a new network. Once they're in place, the operational costs are relatively low, at least when compared to a WAN. And there can be limited privacy because network administrators typically have full control over every file and resource in the environment. Even files that reside on your computer at your workstation can often be accessed. For example, in a Windows network that uses Active Directory as its network management service, administrators are always able to log on to every client system using their own identity, and they could even take ownership of files that you've saved in your own profile. Maintenance can be quite demanding in a LAN, particularly as the size grows, as there are inevitably software and hardware issues to deal with, as well as users who need technical support. And on the flip side of the limited privacy point, other users might be able to gain unauthorized access to network resources if they're skilled at network intrusion methods, or if they're simply very familiar with other users, they may be able to obtain passwords through social engineering tactics. As for WANs, as initially mentioned, they generally connect systems over much larger distances, such as from city to city or even internationally. And as such, they generally require the infrastructure of private telecommunications providers or the internet to facilitate communication over such geographically separated areas. WAN advantages include support for multiple technologies, in that if you have LAN 1 connected to LAN 2 over a WAN, virtually every device in either LAN can communicate with any other type of device in the other. In other words, the WAN doesn't really concern itself with what type of traffic is passing over it, although administrators can configure restrictions if desired. The geographic reach is effectively global, including areas that otherwise could not be serviced, because WANs support the use of wireless communications such as satellites. So even areas with no wired infrastructure whatsoever can still be connected. And just like sharing in the LAN, files, resources, and applications can still be shared, but over a much larger area. Disadvantages of WANs will almost certainly include the cost, particularly if you're using dedicated leased connections from your telecommunications provider or using satellite services. Maintenance might not be as frequent as in a LAN, but WANs typically require specialized equipment, which in turn requires specialized personnel, which can also contribute to higher costs and result in longer wait times before issues are addressed. And even when the appropriate personnel are present, problem solving can be complicated because of the nature of the infrastructure and the equipment used. And since most WANs are implemented using the publicly available lines of the telecommunications provider or the internet, security can be a concern because your data might be flowing over wires that are accessible by many outside of your organization, and you don't control its management. For a summary comparison, LANs are used when coverage is only required over a small area. Speeds are very fast these days, usually 1 gigabit per second or higher. The connection devices used are typically switches or possibly hubs if cost is a concern, although hubs are not commonly used these days. The layers listed refers to the layers of the OSI model, which was covered in an earlier presentation, and in short, Layer 2 is aware of MAC addresses, which makes them much more efficient than hubs, which operate at Layer 1 and aren't aware of any addresses, so they broadcast everything that comes in over one port out every other port. Switches make direct and separate connections between any two communicating systems. LANs are typically very reliable due to their smaller relative size. Their maintenance is typically straightforward in that administrators don't require the specialized training needs that WANs do, and they offer a relatively low cost. WANs have a much broader reach, up to and including global, but due to that and the use of publicly accessible infrastructure, they're much slower than LANs, maybe around 150 megabits per second, and they rely on Layer 3 devices or routers because WANs don't connect computers together, they connect networks together, and routing and other WAN devices are much more complex than switches. Their reliability is more subject to external factors due to the fact that you're using someone else's infrastructure, and maintenance can be much more complicated, again due to the specialized equipment in use and the fact that an issue could arise anywhere within the network of the telecommunications provider. In other words, an issue thousands of miles away could still impact your WAN, and of course the cost can be very high. Other types of network configurations that are related to LANs and WANs include the Personal Area Network, or PAN, the Metropolitan Area Network, or MAN, the Storage Area Network, or SAN, the Campus Area Network, or CAN, and the Global Area Network, or GAN. Personal refers to a collection of devices usually connected to each other using Bluetooth. For example, if you have a laptop, a smartphone, and a tablet that can all synchronize with each other, that is one example of a PAN. Metropolitan falls somewhere in between a LAN and a WAN and might be used to connect networks in separate buildings within a city, for example, all branches of a bank in the same city. Storage area networks are dedicated to storage, as the name indicates, which refers to a collection of servers that can all access the same array of storage drives, so they aren't used for connecting computers together like a LAN. As the name indicates, a campus area network is used to connect all the buildings on the same school campus, such as a large university, And a global area network is effectively just a larger implementation of a WAN, but they typically include wireless technologies such as satellite to provide the widest coverage possible. For most of us, the LAN will by far be the most common network configuration encountered on a day-to-day basis, and the PAN is certainly growing in popularity due to the prevalence of mobile devices these days. But one way or another, for computing devices to be most effective, they need to be able to communicate with each other using some form of networking. So choosing an appropriate networking model will simply come down to your needs, but with cost and other considerations always kept in mind. In this presentation, we'll outline the role and features of IP addresses, where the IP is the same IP of TCP/IP, and it simply stands for Internet Protocol, but its function is to provide a unique address to all devices that reside on the same TCP/IP network, so that any given device can be identified. And this even extends to devices that are directly connected to the public internet as well. Now, just to quickly clarify, the term unique in this context is correct, but I also mentioned that the address only needs to be unique within the same network. In other words, if I have a network and you have a network and they're completely isolated from each other, then we can in fact have devices within our respective networks that do use the same addresses. And if you're familiar with IP addresses at all, you may have realized this already. For most of us who have high-speed internet at home, at least within North America, you may have noticed that devices in your home have addresses such as 192.168.1.10. And if you then go to a friend's house and connect to their Wi-Fi, you might get a similar or even the exact same address. Now, this is due to a lack of available addresses worldwide, and we're going to examine that more closely in the next video. But more to the point, it's due to the fact that there are two categories of IP addresses, public and private. Public addresses are used by devices that need to have direct connectivity to the public internet, such as web servers. But private addresses can be used by anyone within a LAN environment for devices that don't need direct connectivity, which is the case for most of us at home. The router that gets installed in our homes is the only device that is directly connected to the internet, but every router has at least two interfaces, one that connects outward to the internet and one that connects inward to the LAN. And for the inward side, certain ranges of addresses have been reserved for internal use only, and they're largely the same on most of these devices and pre-programmed in, which is why we so commonly see addresses such as 192.168.1.10, because all addresses that begin with 192.168 are reserved for that internal-only configuration, and all reserved private address ranges are never forwarded out to the public internet. In short, all routers are pre-programmed to recognize internal addresses as being internal, so they are never routed to the public side. Now, there are other reserved ranges, but this is what allows a device on my network to have the same address as a device on your network, because again, they don't directly access each other on the public internet. So regardless of how many devices you have in your home, they can each use a private address. But when they do need access to the internet, they go through the router, which is the only public address needed. But those public addresses do need to be unique. So the public address of my router, which is assigned to me by my internet service provider, would indeed be different from the public address of your router. But by using private addresses on the internal LANs, we can greatly reduce the number of public addresses that are required to be issued. Plus, private addresses can also provide better security for our LANs because only a single interface is directly connected to the public internet as opposed to every device on the network. IP addresses operate at the network layer of the OSI model, which, among other things, defines the ability for packets to be routed from network to network. And it's worth noting that every IP address actually has two parts. The first part of the address identifies the network on which your system resides, and the second part is your device or host address on that network. A good analogy for that is to think about all the houses on the same street. Each house has a unique number, but they all reside on the same street. So one part of the overall address is the same for all houses, but another part is different for each one. As a more practical example, coming back to standard home internet, if your desktop computer has an address of 192.168.1.10, your mobile phone might have an address of 192.168.1.11, and your tablet might have 192.168.1.12. In this example, all devices share the 192.168.1 portion, but 10, 11, and 12 uniquely identify each device. In other words, 192.168.1 is the network address, and 10, 11, and 12 are the host addresses. Now, that's only one example. There are different configurations for different networks, but the two-part address is always the case with IP addresses. The address itself is always an inherently numeric value, even when using IP version 6, which includes letters in the way it displays. Now, IP version 4 only uses numbers in the display, but more accurately, both types of addresses are binary in nature, meaning that they're collections of ones and zeros. The values that we see, such as 192.168.1.10, just make it easier for us to recognize and work with. But every device that needs to communicate on the network will be assigned an address, including devices such as printers, the inward router interface, firewalls, and of course all computing devices. And at home, even devices such as thermostats, TVs, gaming consoles, smart plugs, digital assistants, and many others will all receive an address. Now, I mentioned a moment ago how the public interface of your router is assigned its address by your internet service provider. But where do they get those addresses from? Clearly, we can't all just decide which addresses we want to use on the public internet, because that would almost certainly lead to duplicate address use. So internet service providers and various other organizations that need large banks of public addresses are assigned ranges that they can use by the Internet Assigned Numbers Authority, which itself is a division of the Internet Corporation for Assigned Names and Numbers, which is a nonprofit organization based in the United States, but they distribute large ranges of addresses to regional internet registries, which can then distribute addresses at their discretion within their region. The regional registries will in turn assign smaller ranges to organizations such as internet service providers, who can then distribute any value within their range to their customers at their discretion. So the addresses we receive certainly aren't random. They have to be very carefully managed to ensure that no two entities receive the same addresses or ranges that overlap. For any internal private network, though, we are all free to use any addresses within the reserved private address ranges, which again is why we see values such as 192.168.1.10 being used so frequently. Now, all of that said, while using private addresses allows us to reuse the same address ranges, that doesn't mean that everything is taken care of for us. Individual devices within any given network still have to be assigned an IP address, and the addresses that we use still have to be managed, particularly in a very large network. Now, you might be thinking to yourself that in your home, all you have to do is connect a device to your Wi-Fi and that's it. Every device has internet access. While that's true, it's because the router, once again, is pre-programmed to do that. But in corporate networks, administrators have to determine which ranges of private addresses should be used within which areas of the network, and they have to make sure that no two devices end up with the same address, which would cause what is known as an IP conflict, which will typically render at least one of the devices unable to communicate. Now, with respect to the IP address assignment, there are two options. Devices can have their addresses assigned manually or automatically through a service known as Dynamic Host Configuration Protocol, or DHCP, which is the service that runs by default on our home routers. But in networked environments, administrators must install or activate the DHCP service on specific servers or routers, and they must decide which systems will be serviced by DHCP, which is typically all standard client systems, but servers, routers, printers, firewalls, and other network devices are commonly configured manually because with DHCP, your address is typically only assigned for a certain period of time, such as a week, after which time it's entirely possible that you'll receive a different address. But any device that is configured manually will keep the same address indefinitely until someone manually changes it. This leads to greater reliability in terms of systems being able to consistently contact those more important systems, so to speak. But it can also lead to errors in configuration if a simple typo is entered by mistake, or a conflict might arise if two devices are mistakenly configured with the same address. Now, DHCP greatly simplifies the address management process because a pool of addresses is defined from which addresses are allocated to all client devices automatically when they boot up. And as long as the pool is configured correctly, a DHCP server will never issue the same address twice. But in large networks especially, you might have to manage many DHCP servers, and any type of problem with the network might render clients unable to communicate with the DHCP server. So, IP address assignment and management is a significant part of network administration in many environments. For most of us at home, we generally don't have to deal with it because, again, our routers come pre-programmed with a DHCP pool already activated, so all we have to do is connect to the Wi-Fi or plug into one of the Ethernet ports. So for everything else that is involved with networking, and for all the enhancements that networking brings to the world of computing, in essence, it all comes down to the IP address, because without it, you can't communicate at all. Now, that said, there are other protocols and other ways of networking, but for the day-to-day communication needs of almost all of us, having a valid IP address is required to be able to network in just about every environment. In this video, we'll compare and contrast IP versions 4 and 6, both of which are in use today, even though version 4 has been around for decades. Now, you might be wondering what happened to IP version 5. Well, in short, it was being developed, but for starters, IP version 4 uses a 32-bit address, meaning that there are 32 ones and zeros in total, which provides for 2 to the power of 32 possible addresses, which is approximately 4 billion unique values. Now, while that might sound like a lot, there are already more devices than that in use today. Plus, many of the IP addresses of version 4 are not used for public internet addresses. So, in practice, there are far less than 4 billion available. As such, all public addresses in version 4 have in fact been exhausted. Now, that doesn't mean you won't be able to get access to the internet if you call your internet service provider for a new hookup. They would have addresses available, but they've been assigned a block or a range of addresses that they can use at their discretion. So while any given address might be available to us when we sign up, the address has already been assigned to the ISP. So it is therefore considered to be already assigned. But coming back to IP version 5, it was originally being designed as a streaming protocol that also used the same 32-bit address. But it was becoming clear during its development that it would end up facing the same exhaustion issue as version 4. Hence, it was shelved, and version 6 was designed in its place with a much larger address space and enhanced functionality, all incorporated within the protocol itself. Now, the exhaustion of the version 4 address space came about because in the early days of the internet, it was never anticipated that it would grow into what it is today. In fact, it was never even envisioned that it would become a publicly used network. But by the late 1980s, it was becoming clear that even billions of addresses would not be adequate to publicly address every device on the internet. And today, there has been an explosion of devices and applications that require internet connectivity, and demand is only anticipated to grow more and more rapidly. So, in short, a new standard is required. So the number of available addresses comes down to the length of the address itself. And as mentioned, version 4 uses 32 bits for each address. Now we don't see ones and zeros. We see values such as 192.168.1.10, but in fact, those are just the decimal equivalents of the underlying binary values. For each value that is separated by the period, there are 8 bits in use. Since there are 4 values, each one requiring 8 bits, that's 32 bits in total. Within each 8-bit section, which is also known as an octet, each bit is assigned a positional value. And if the bit value is 1, then the numeric value is added to the total. But if the bit value is 0, the numeric value is not added. The first bit, as read from left to right, is worth 128, then 64, then 32, then 16, then 8, then 4, then 2, and finally 1 for the 8th bit. So if you've ever looked at an IP address and wondered why you never see a single value such as 260, it's because if you add up all the bit values, in other words, if all bits were set to 1, then the highest value you can get is 255. Now, this also comes down to the fact that if you have 8 bits to work with, then the total number of possible combinations that can be used is 2 to the power of 8 for any single value, which is 256. But if all bit values are set to 0, then the numeric value is also 0, and 0 counts as far as computers are concerned. So the range of possible values goes from 0 to 255. With 0 included, that's 256 values. And since there are 4 octets, as mentioned, that's 32 bits in total. And 2 to the power of 32 is approximately 4 billion. But as we've discussed, that's simply not enough addresses for today's world. So IP version 6 uses an address that is 128 bits long. At first glance, that might seem like it's only 4 times as large, but not when you're working with binary and exponents. For each increment of the exponent, the total number of possibilities doubles. So 2 to the power of 33 is twice as much as 2 to the power of 32, or around 8 billion addresses. 2 to the power of 34 is twice as large again. So 2 to the power of 128 is virtually unimaginably large. But to put a value on it, it's over 340 trillion addresses. So for anyone who might think, well, we've underestimated before, it'll just happen again eventually, I'd say that it's safe to say that this address space will never become exhausted. In a more imaginable context, IP version 6 provides enough addresses for every single person alive today to be allocated about 6.5 billion addresses for their own personal use. That immensely larger address, however, also requires a different method of display for day-to-day use. Even in version 4, it's too difficult to work with 32 ones and zeros. So, as mentioned earlier, we use binary to decimal conversions to display that value to us in more meaningful and easier to work with numbers. But with 128 bits, that would still result in a decimal value that's just too large. So hexadecimal characters are used in groups of 8 with 4 characters in each group. And if all bit values in each group are set to 0, then a single 0 in hexadecimal can be used to shorten the overall value. Now, while IP version 6 does solve the exhaustion issue, it's still a very long value to work with. Values in IP version 4, such as 192.168.100.1, are relatively easy to remember should the need arise. But it would be very difficult for most of us to remember even one IP version 6 address. So name resolution services such as DNS become even more important so that we can rely on referring to systems by name instead of by IP address. Now that said, DNS is already a critical service in almost every environment, but it's just that little bit extra important, so to speak, with IP version 6. So So when it comes to making the transition to IP version 6, it comes down to the devices themselves, and more to the point, the operating systems they run. But most devices these days already fully support the use of version 6, although due to version 4's prevalence and relative ease of use, it remains in use in almost every environment. So dual support is the more common configuration for devices these days, with version 6 just being the default. In other words, if there are two devices that both have both protocols installed, version 6 will be used to communicate unless an application or a service specifically requires version 4, but both will work. But it's worth checking the status of the devices, operating systems, and applications in use in your environment to verify their protocol support. Any system or application that is version 6 unaware means that it requires version 4, and version 6 simply isn't supported. Version 6 aware means that it is supported, and version 6 is preferred, but it still supports version 4. Version 6 enabled is similar to aware, but can only interoperate with version 4 in a diminished or reduced functionality mode, and version 6 required is exactly that. Version 4 is not supported. Eventually, version 6 will replace version 4, not only because of its larger address, but functionally version 6 has features that make it a more robust protocol as well. But for the time being, you're likely to encounter both in many environments. But for most of us, at least in terms of day-to-day use, it's likely that version 4 will be the more referenced address. In this video, we'll examine the role and characteristics of the Media Access Control, or MAC address, which is a unique value that is assigned to every device that is capable of connecting to a network, and it consists of a 12-character hexadecimal value in 6 groups of 2 characters each, with each group separated by a colon. Now, when I say that the value is assigned to every device, in fact, it's built right into the network interface itself as a unique identifier in the form of a read-only memory or ROM value that never changes over the lifespan of the device. Now, there are software applications that can clone, mimic, or otherwise translate MAC addresses into other values, but the inherent address of the interface itself does not change, and every network interface card has one. As such, all other forms of addressing, such as IP addressing, ultimately rely on the MAC address because it's the only truly unique value when it comes to addressing. A typical MAC address looks like the example on screen. As mentioned, 12 characters in total, but with hexadecimal, both letters and numbers can be used, with numbers ranging from 0 to 9 and letters from A to F, for a total of 16 characters, which is the base value of hexadecimal. Hence, it is also sometimes referred to as base 16. Now, 16 characters can be expressed in binary using only 4 bits, because 2 to the power of 4 is 16 possible values. So each group of 2 characters in binary requires 8 bits, meaning that the total length of a MAC address is 6 groups times 8 bits per group, or 48 bits, meaning that in total, 2 to the power of 48 possible MAC addresses exist, which is about 281 trillion possible addresses. So we're not in any immediate danger of running out. MAC addresses operate at the data link layer of the OSI model, which in fact was ultimately divided into 2 more specific sublayers, one called the logical link control, and one actually called the media access control, which is where the name originates. And this is the first layer of the OSI model where any kind of addresses can be defined. But despite the fact that the data link layer is a layer above the physical layer of the OSI model, it is often referred to as the physical address. But this isn't in reference to the OSI model. Rather, it's due to the fact that, as mentioned, the address is written directly into the device itself by the manufacturer and essentially becomes an attribute of the physical device, just like its size and shape. Manufacturers themselves are assigned blocks or ranges of MAC addresses that they can use at their discretion. They just need to ensure that they don't ever assign the same address twice. The term physical address is also useful for distinguishing it from an IP address, which is also referred to as a logical address, most notably because the IP address that is assigned to any given network interface can be changed at any time, whereas the MAC address can't. Logical addresses operate at the network layer of the OSI model, which is the layer immediately above the data link layer. So again, this distinction helps to separate the functionality of each type of address. While the MAC address might not be referenced all that much in day-to-day networking, it's still beneficial to know how to locate it, particularly when troubleshooting network connectivity problems. Now, it will depend on the device and the operating system on that device, but MAC addresses are usually found somewhere in the device's system settings or through applications such as command prompts. As a practical example, if you're on a Windows system, you can launch a command prompt and enter the command ipconfig, all one word, then optionally a space, then a /, followed by the word all, ALL, with no spaces between the slash and the word all. In the results, you'll find an entry that in fact is listed as physical address as opposed to MAC address. On a Windows 10 device, you can also go to Settings, Network and Internet, click Properties under the Ethernet connection and scroll to the bottom of the page and you'll see physical address, again, but with MAC in parentheses. On an iPhone, you can go to Settings, General, About, and you'll likely see MAC addresses for both the Wi-Fi connection and possibly Bluetooth. So if every network-capable device has a MAC address, why do we even need an IP address? Well, it comes back to the OSI model, because MAC addresses only operate at the data link layer. They are unaware of the network layer. Now, that doesn't mean that a MAC address isn't capable of participating on a network, but it does mean that they themselves do not understand internetworking. To put that another way, switches also operate at the data link layer, so they understand and operate based on MAC addresses, so they can connect computers together to form a single network without the need for IP addresses. But routers operate at the network layer and require IP addresses. And since routers connect networks together, not computers, in order for any computer on one network to communicate with any system outside of that network, for example, the internet, you must use IP addresses and routers. But as mentioned, IP addresses are logical, meaning that they can be changed. So the two addresses can work in combination with each other through the use of another protocol within TCP/IP known as the Address Resolution Protocol, or ARP. And it's ARP's job to resolve any given IP address to the MAC address of the adapter to which that IP address has been assigned. So when my computer needs to communicate with your computer by using an IP address, ARP will first determine that IP address X is currently bound to MAC address Y, and once that resolution has been performed, we can begin communicating using the higher level IP address. In fact, if you're on just about any kind of network right now, and you're on a Windows computer, you can launch a command prompt and type in ARP, A-R-P, space -A, and you'll see a list of IP addresses that have already been resolved to MAC addresses, because you've already initiated some kind of communication with those other devices on your network. So while the IP address is likely the one that most of us are much more familiar with, in fact, the MAC address is the foundation of all addressing, so it's certainly worth knowing its basic characteristics. In this video, we'll take a look at the Hypertext Transfer Protocol, or HTTP, and its secure implementation, HTTPS. Now, beginning with HTTP, it's a protocol that many of us might be at least somewhat familiar with because it's the primary communication protocol for accessing websites. And perhaps more to the point, it permits our web browsers to communicate with the servers that host web pages and web-based applications. So if you've ever launched a browser and accessed any given website, you may have seen the letters HTTP or HTTPS prefacing the address. Now, some browsers don't actually show the letters, but they're simply being suppressed from the display. The protocol itself is most certainly still being used. Both HTTP and HTTPS operate at the application layer of the OSI model, which is the highest layer and essentially means that it is used by an application, most commonly a browser, to indicate which type of service is being requested of the server. For example, a web server can often do more than just serve up web pages, but the server does not specifically know that we as clients are making a request through a web browser, but it does see the request as coming in over HTTP, in which case the server now knows that we are specifically asking for its web page. Now, while browsers are certainly the most common applications to use HTTP, they aren't the only ones. For example, if you're part of a corporate environment using internally hosted email, while you're in the network, your email application likely uses SMTP or Simple Mail Transfer Protocol to communicate with the mail server, but without specific security configurations or the use of something like a virtual private network, SMTP can't be used outside of your network to access your mail servers, but you can likely use that same email application to access your email even when you are outside of the network by using HTTP or more likely HTTPS. In terms of its basic characteristics, HTTP is referred to as a stateless protocol, which means that each transaction or request is executed separately from any others, and no connection is maintained between the client and the server for any possible upcoming transactions. In other words, you open your browser, you request a site, the site is delivered, then the connection is closed. If you then click on a link on that site, the process invokes an entirely new transaction and the same process occurs. The protocol operates over TCP port 80, which is a more official way of identifying the protocol as HTTP to the server. But port numbers are also used with firewalls to ensure that appropriate protocols are allowed to pass through, while others are not. So the firewall will examine the port number of the protocol to determine if it's allowed. A good way to think about port numbers is to imagine them like extensions for phone numbers. You might call an office of some kind whereby there is a single phone number for the office or company as a whole, but you can then dial an extension to reach a specific person or department. In TCP/IP, the IP address only indicates the server as a whole, similar to the company's phone number, but any given server can supply many different services, so the port numbers indicate the specific application layer protocols, just like extensions are assigned to specific people or departments. Now, HTTP in its basic state, for lack of a better word, does not provide any kind of security. In some cases, this isn't an issue though, because if all I'm doing is going to the internet to view a website, and I'm not providing any information to that website, then I don't really need any kind of security. I'm just viewing information. But these days, many sites and web-based applications require data back from us, in which case we don't want to be submitting personal data over the public internet without protection. Hence, HTTPS is a secured form of HTTP that uses encryption to protect data during transfer. HTTPS is identified to servers and firewalls over TCP port 443, and you should look for the use of HTTPS on any site that wants you to submit information back to the server so that it can't be intercepted by a malicious user. But virtually every modern browser will provide some kind of indication that the site does use HTTPS, either in the address line itself by specifically displaying the letters HTTPS, or by displaying a padlock icon, or both. Some of the most common examples of its use include online banking or making online purchases with a credit card. Clearly, we want to feel secure in submitting that type of information over the public internet, so you should always verify the use of HTTPS in the browser before any information is submitted through that site. The components of HTTPS that provide the security are two additional protocols known as Secure Sockets Layer, or SSL, and Transport Layer Security, or TLS. Now, from a standard user's perspective, both protocols essentially provide the same service, which is to encrypt communications over HTTP, but TLS is a newer protocol than SSL and is generally considered to be more secure, so it's largely the standard in use for today's secured sites. The encryption mechanism used to protect the data uses a combination of mathematical algorithms known as encryption keys, with two separate keys being used. As such, they're also referred to as asymmetric keys because each one is different. Private keys are held by the organization hosting the site, and as the name indicates, they're held by that organization and only that organization. Public keys are issued to the general public for use on our local devices. So when we access the site, the public key is downloaded to our computers, so anyone can get a public key, but anything that is encrypted with the public key can only be decrypted by the private key. But that in itself would only provide for one-way protection from my computer to the server, because if the server then needs to send back secure information to us, such as our bank balance information, it would not have the same public key that we just used. So a third key is actually created by our own local computers, and that third key is referred to as a symmetric key, because we'll use the public key that we just received to protect the third key that we just generated. Then we send that protected key back to the hosting server. Since that third key was encrypted by the public key, it can now only be decrypted by the private key, which is only held by the servers of the organization. So the hosting server is the only entity capable of unwrapping that key, so to speak. But it was originally generated by our own local computers, so we already know what it is. But now both entities know what that third key is, so it's now referred to as a symmetric key, and that's the key that is actually used to protect the two-way communications between our systems. Finally, SSL and TLS provide more than just encryption. They also provide the ability to validate the identity of remote servers through what's known as certificates, which ensure us as users that they are a legitimate organization who have been properly vetted and have demonstrated that they're trustworthy and that they are who they claim to be. That validation is implemented at 3 levels, including domain validation, which ensures that the person requesting the secure site actually owns the domain name in question; organization validation, which ensures that the owner of the organization is who they claim to be. In other words, if I'm applying for a certificate for AaronSampsonEnterprises.com, then domain validation would ensure that the domain is owned by Aaron Sampson. Organization validation would ensure that the company of Aaron Sampson Enterprises is in fact owned by Aaron Sampson and that I am Aaron Sampson. Extended validation is the highest level, so to speak, and would include verifying the proof of business registration in the first place. Now, these validations are performed by other organizations known as certificate authorities, and it's basically their job to investigate us. And if everything is in order, then we're issued our certificate, which is then incorporated into SSL and TLS secured communications, and it indicates to the general public that we have been validated. Now, that in itself does not guarantee that an unscrupulous user can't go through that whole process legitimately, then use their certificate for malicious purposes. But for major financial institutions and other very well-known retailers or merchandisers, as long as you see the use of HTTPS on their sites, you can largely rest assured that your data will safely traverse the internet. In this presentation, we'll compare and contrast some common email protocols, which are designed to facilitate email transmission between a mail server and a client. Now, there are several email-based protocols in use, but the specific protocols that are used will depend on the environment and the email application that is being used. So, two common examples are the Post Office Protocol version 3 or POP3 and the Simple Mail Transfer Protocol or SMTP. Now, just quickly, both protocols have been around for quite some time now, decades in fact, but I will tell you that POP3 is certainly still in use, but it's becoming a little less common these days. But SMTP is still one of the most commonly used mail protocols, and again, their use will depend on the circumstances. So, beginning with POP3, for starters, this is a receiving protocol only, and its most common implementation these days would be for home email accounts that are hosted with your internet service provider. So, in many cases, when you subscribe to internet services from your local provider, they'll offer you an email account or perhaps several. But in short, they'll create mailboxes for you on their servers. So if I were to send you an email, that message would arrive in that server-based mailbox until you launch your local email application and then click on Send and Receive. At which point, POP3 is used to download the messages from the server to your local client. But while that will work just fine, it's important to note that messages are downloaded to the local client application that you just used and only on that device. In other words, if you have, let's say, a desktop computer at home and a smartphone, both with the same email account set up on those devices, which you can do, and then you download the messages on the computer, those same messages will not be available on the phone. Then, if you do the exact opposite the next day and check your mail from your phone, any messages that are received will not be available on your desktop. Now, that said, that's just the nature of the protocol itself, in that all it's concerned with is downloading the messages. There are features within various email applications whereby you might be able to specify that when messages are downloaded, a copy should remain on the server for a certain number of days so that if and or when you do check your mail from other devices, the server-based copy will still download to those other devices. Or you might also be able to configure synchronization between your devices so that they'll remain consistent with each other. But those are features of the applications and or the devices, not the protocol itself. So this is one of the reasons why POP3 is starting to become less commonly used. Web-based email services such as Gmail or Outlook.com only ever keep the mail on the mailboxes of the server. They're never directly downloaded to the client device, so no matter which device you use, you're only ever seeing the server-based messages, so your mail is always consistent. In addition, while very large national-level providers are likely to remain in business, there are many startup-level providers that attempt to offer discount internet services who might also offer email. But if they go out of business, your email address hosted with them goes away as well. POP3 does support security in that the server requires authentication in the form of a username and password, and once your credentials have been verified, your messages are downloaded. Now, in almost all POP3 based applications, you can enter the username and password into the application itself so that it will provide those credentials to the server. In other words, you aren't prompted every time you try to retrieve your messages. But it's also worth mentioning that many providers also provide you with web-based access to your mailbox, which is very useful if you're traveling. In those cases, you can simply use a browser to access your email, but in that situation, you do need to supply your username and password each time you access the mailbox. So you should ensure that you remember what your password is. If you only ever configure it into your local email application one time, then use nothing but that application, it can be easy to forget what it is because you aren't prompted each time. So in some cases, it could be months or even years before you're ever prompted for your password again, as most providers do not require you to change your email password regularly. Now, SMTP is kind of the opposite of POP3 in that it is used for sending mail, not receiving it. And SMTP is one of the most widely supported mail protocols, regardless of the email client application being used. Now, I'll expand upon that in just a moment, but let's just go back to the home email situation whereby you have a mailbox with your internet service provider. As mentioned, POP3 is used to retrieve your mail, but POP3 does not send. So if you have ever configured an email application for use with these types of home email services, you were almost certainly required to enter in the name of your incoming mail server and your outgoing mail server. The incoming might have been something like pop.myprovidersname.com, and the outgoing might have been something like smtp.myprovidersname.com. Now, despite those two different names, there would most likely only be one actual server. It just has the ability to provide both protocols. But in this configuration, SMTP has some drawbacks. For starters, in its default state, SMTP does not require authentication. Now, it can be configured to require authentication, but the way that security is approached in most cases is that your system at home is using the network of the provider. So, as a paying client, you're allowed by default to send email through the server of that provider. But of course, people who aren't paying customers of that provider are not allowed to use that server. If they were, those email servers would quickly be identified by spammers, and they'd be co-opted to send out huge volumes of junk mail. So in short, if you're on the network of the provider, then you're able to send mail through their servers. But if you're not on the network of the provider, then you can't. Now, this likely would never be a problem for a home desktop computer because it doesn't move, but it can be very problematic for mobile devices. As soon as you connect to something like a public Wi-Fi, if that wireless network is not using the same provider as you, then you're on someone else's network and you won't be able to send any mail, because from the perspective of the provider, you're just some anonymous user on some anonymous network. Now, as mentioned, SMTP can be configured for security and authentication so that you can send from other networks, but that usually isn't the default configuration. Another option is to have multiple SMTP servers configured in your email application. And in fact, I'll give you a specific example. I do have an email account with my internet service provider that I still use, and its default configuration is exactly how I just described. But I do have a laptop that primarily stays at home and a mobile phone configured with the same email account. So while I'm here at home, I can send from either device without issue. But as soon as I leave home with my mobile phone, access to the internet is of course still available through my mobile phone service provider, who is not the same as my internet service provider. But while I'm using my mobile phone away from home, my device is on their network. So just like my home internet service provider, while I'm on the mobile phone provider's network, I am allowed to use their email servers to send mail. So on my phone, I have a primary SMTP server configured, which is the server of my home internet service provider, and a secondary SMTP server, which is the server of my mobile phone provider. So when I leave home, it will try to send through my home service provider, but it will fail. However, it will then try the secondary server and it will succeed. So I'm able to send in either situation, but then if I do connect to something like a public Wi-Fi, I have no idea who the internet service provider is in that case. So in order to send mail, I have to make sure that I disconnect from that Wi-Fi and use standard cell service to be able to send. This also raises an issue similar to that of POP3, whereby if I send a message from my phone, that message does not show up in the sent items folder of my laptop unless I configure synchronization. So this is yet another reason why these home email accounts are becoming less common. So I mentioned that I'd expand upon SMTP's use, particularly because that previous scenario can make SMTP sound like a rather cumbersome protocol, despite the word simple being in its name. But where SMTP is very effectively implemented is in corporate networks, in which case it acts less like a send-only protocol and more like a movement-only protocol. In these environments, messages are quite literally just moved from server to server, and the client applications we use do not use something like POP3 to download the messages to our local devices. We just use our email applications as portals, so to speak, to view the contents of our mailboxes, but those mailboxes reside on the server, and they only ever reside on the server, as do all messages in those mailboxes. So if you and I both work for the same organization and I send you an email, my mailbox might reside on server 1 and yours might reside on server 2. So while I'm composing the message, again, I'm only viewing the contents of my server-based mailbox, and when I hit send, the message will be retrieved from my outbox and delivered by server 1 to your inbox on server 2. When you then open your email application, you're likewise only ever viewing the contents of your server-based mailbox. So the message is not downloaded to your local device, hence POP3 is not used. All messages in this type of environment are simply moved from server to server, and even if there is only a single server, the exact same process still occurs. It just moves the message from my outbox to your inbox, and we all simply use our devices to view the contents of the messages that reside on the server. So this eliminates the issue of having inboxes and outboxes that are out of sync with each other across multiple devices. We can use as many devices as we want, and the contents of our mailboxes will be identical in every case because nothing ever resides on the local devices. Everything is retained on the servers, so in this implementation, SMTP is indeed a very simple and user-friendly protocol. To finish up, since each protocol does perform different tasks, they're identified to servers by using port numbers. And POP3 by default uses port 110. So if you have ever set up a home email service, then you might have noticed that port value when you're entering the name of the incoming mail server. And SMTP by default uses port 25. Now, as mentioned earlier, POP3 does require authentication in the form of a username and password, but messages are not transferred using any kind of encryption. But POP3 can be secured using either TLS or SSL, just like HTTP can, in which case secured POP3 uses port 995. Likewise, SMTP can use port 465 for an implicit secured connection, but 465 has largely been deprecated in favor of port 587 as the preferred port for secure SMTP, and 2525 is often used as an alternative to 25 for when encryption is supported but not required. If you do have to set up a local email application for use with home internet, then your ISP will almost certainly provide you with all appropriate server names and ports, but if you're in a corporate environment, then your email will almost certainly be configured automatically by your network administrators. So all you have to do is log into your computer and start using email straight away. Now, just to quickly finish up, while I touched on web-based email services such as Gmail and Outlook.com, which are certainly great options for most home users, similar functionality is also provided by corporate email environments and even home email providers. Most corporate environments will provide you with web-based access to your mailbox so that you can access it from anywhere. And even if you're just a home user, you're likely also able to access your mailbox from anywhere by just using a browser. But once again, for home email, if you do access your mailbox from something like a browser on a hotel lobby computer, while your received messages will still download to your local devices when you get back home, anything you send would have been sent directly from the mail server itself. So that sent message will not appear in the sent items of either your home computer or your mobile phone. So if you feel that you'll need a copy of that message on your own personal devices, then it's a good idea to send a carbon copy to your own address. Then at least you'll have a record of it. In this video, we'll provide an overview of the Internet Message Access Protocol, or IMAP, which might also be referred to as IMAP 4, which is the current version. Now, IMAP allows you to access and manage email messages and is commonly used as an alternative to POP3. But like POP3, IMAP is a receive-only protocol. In other words, SMTP is still required for IMAP accounts in order to send mail. But POP3, by comparison, is a somewhat limited protocol, in that when you retrieve your messages, all messages that have arrived in your mailbox since the last time you checked are delivered, and they're all fully downloaded to your local client device, at which point they are also removed from the server. So they only ever ultimately reside on that local device. Now, I will qualify that statement by saying that's if your email application has not been configured to leave copies on the server, but that's a function of the application, not the protocol. By contrast, IMAP messages remain on the server by default, which makes those same messages available from multiple devices, eliminating the need to configure synchronization across those devices. By leaving messages on the server by default, IMAP also facilitates easier searching of messages across devices because your mailbox will be consistent in all cases. And if you permanently delete a message, it would be deleted from every device. Now, of course, more accurately, it's not really deleted from any device because it only resides on the server, but from our perspective, it would be gone on all devices. You can also create and manage folders for easier mail management. Now, to qualify that statement, you might have a POP3 account set up as your home email, and your email application would almost certainly allow you to create folders to help organize your mail. But those folders in that configuration are just on your local device. And if you had two devices, you would either have to recreate the exact same folders on each one, or again, implement some kind of synchronization. But folders in IMAP are on the server, not the local device, and you could specify that if you do want to download messages to any given local device, that only the contents of a specific folder be downloaded. So in other words, if you had even two folders created on the server with, let's say, 5 messages in each one, you could download just the 5 messages of one folder if you wanted to, leaving the other 5 on the server. Again, POP3 only ever delivers every message to a single inbox. It's then up to you to move them to the appropriate folders on your local device. If configuring an IMAP account on a local device, it uses port 143 by default for unencrypted transfers, or port 993 for secured connections using TLS or SSL. Again, for a home email account through a local internet service provider, they would provide you with the appropriate server names and port numbers. But in terms of basic functionality, IMAP can provide several advantages over POP3 because messages are retained on the server by default. Now, I should reiterate that you can download messages to any given local client device using IMAP, and if you were to do so from different devices at different times, then you could still end up with inboxes that are not consistent with each other. But at the server level, any changes that are made from any client, such as deleting a message, are reflected in real time, and you would see those changes immediately across all devices, regardless of which device was used to make that change. So if messages are never downloaded to your local devices, then your mailbox will be consistent no matter which device you use. However, if that's the case, then you might also need to be mindful of the size limits of your mailbox. Many providers might implement a limit on the size of the mailbox overall. So if every message is kept on the server, you could easily reach your limit in a short amount of time, in which case messages will have to be either deleted or downloaded to at least one of your local devices. But IMAP's default behavior of keeping messages on the server can provide a more consistent and user-friendly email environment than POP3. In this video, we'll outline the various types of networking devices along with their basic features, beginning with the modem, And its name is actually a contraction of modulator and demodulator, which refers to the fact that digital signals have to be manipulated so that they can be transmitted over inherently analog lines. Now, early modems were actually implemented as an expansion card that was inserted into your computer or as an external device, but in either case, the modem connected directly to your standard phone line, and you literally use that to make a phone call to your internet service provider to provide you with access to the internet. And once connected, all data was sent and received using that standard phone connection. For the younger viewers out there, you fortunately never had to experience these types of connections because their maximum speed was barely 50 kilobits per second. Just for reference, if you had a cable or a DSL connection that offered even 50 megabits per second, that's 1,000 times faster. And a modern 1 gigabit per second connection is 20 times faster than that again. In other words, a 1 gigabit per second connection is 20,000 times faster than the old dial-up speeds that were available back when I began my career in IT. That all being said, fortunately those types of modems disappeared long ago, so the more common implementations are those provided to you by your internet service provider, which use either cable TV coaxial cable, commonly referred to as cable modems, or DSL, which stands for Digital Subscriber Line, which does still use phone lines, but with protocols and devices that can support far greater speeds than dial-up modems ever could. Both cable and DSL can provide you with what is considered to be high-speed internet, and again, both still have to manipulate digital signals for transmission over inherently analog lines, but neither option offers the performance of fiber optic. So if it's available in your area and within your budget, fiber optic internet service would be the best choice these days, followed by cable, followed by DSL in terms of performance. Switches are the devices that relay information to all devices that are connected into that switch, and they can be thought of as a distribution point, so to speak. So, in short, if you and I are both using computers that are connected into the same switch, then we'll be able to communicate with each other. Switches are most commonly found in larger LAN environments where there might be hundreds or even thousands of computers, and switches can be connected to other switches so that everyone can communicate with everyone else. Switches are the successor to hubs, which performed the same basic functionality, but switches are aware of addresses, specifically MAC addresses, meaning that if I want to communicate with you, packets are sent directly from me to you, and no one else receives those packets because the switch knows my MAC address and it knows yours, and it knows which physical ports we're connected to. So when the transmissions are sent, it will pass them directly from sender to receiver. Hubs, however, are not aware of any addresses. Hence, those same packets sent from me to you also went out to every other system connected to that hub. Now, that didn't mean that everyone else saw the information that I was sending. The protocols and devices that were in use were still able to determine that the packets were not destined for them, but they still arrived at your interface. So your system would have to take the time to examine that packet, realize that it was not for them, and then simply discard them. But it was still a very noisy environment, if you will, when hubs were in use. So they've almost entirely been superseded by switches. Routers are similar in that they also relay packets from one place to another, but routers do not send data from one computer to another. Rather, they send data from one network to another. In other words, they allow data to exit your network and enter another. Perhaps the most common example of this is being able to access the internet from your home, or even from a work environment. Your home and or work represents one network, and the internet represents another. So in order to reach that other network, you must have a router. Routers operate at layer 3 of the OSI model, which is the network layer. And like switches, they're also aware of addresses, but at layer 3, it's the IP address that's used, not the MAC address. MAC addresses reside at layer 2 of the OSI model, so routers can be thought of as higher level devices, and they do in fact require much more programming and configuration than switches. But in simpler terms, if you were to take 10 computers and plug them all into a switch, you can rightly call that a network, and all 10 computers would be able to communicate with each other. But if you then take another 10 computers and plug them into a different switch, then you have another network, and each one would be separate and isolated from the other. So if you then want to connect each of those networks together so that each network can communicate with the other, then a router has to be used. Now, you might be thinking, hold on a second. He just said that multiple switches can be connected to each other so that everyone can communicate with everyone else. And that's entirely true. You could do that without a router, but it's the network layer that makes the difference here. Or more plainly stated, it's the addressing that's used. As mentioned, switches operate on MAC addresses, but you and I almost never refer to those or even experience them, at least not very often. But you might be very familiar with the IP address. Well, your IP address not only identifies your computer on any given network, it also identifies which network you're on. So you certainly can just connect those switches together, but in order for everyone to be able to communicate with everyone else, the IP addresses you configure would have to indicate that all systems are in fact on the same network. If, however, the first group of computers used IP addresses that designated them as being on network 1, we'll call it, and the other group of 10 computers used addresses that designated them as being on network 2, then switches cannot just be connected together. You would need a router. For practical values, and this is only one example, in order for all 20 computers to be able to communicate with each other by just connecting them with switches, they would have to be using IP addresses such as 192.168.1.1 through 192.168.1.20. That would place them all within the same network. But if the first group of 10 were using addresses such as 192.168.1.1 through 192.168.1.10, and the second group of 10 were using 192.168.2.1 through 192.168.2.10, then that addressing scheme would define two separate networks, and a router would then be required to connect them. Again, that's only one example, but in that example, 192.168.1 indicates network 1, and 192.168.2 would indicate network 2. So, with separate network addresses, a router would be required to connect them. Gateways, for the most part, can be thought of as routers in that they perform the same function of connecting networks together, but gateways have additional programming and even hardware in some cases that allows them to connect networks of different types, or those that use different protocols. So in more general terms, a router would only be appropriate if the two networks being connected are of the same type using the same protocols, whereas a gateway is more flexible and can translate, for lack of a better word, among different types. Now that said, the term gateway itself has become largely interchangeable with router, because on many devices and platforms, if you look at your IP address configuration, you will almost certainly see a value listed as default gateway, which simply represents the device that allows you to communicate beyond your own local area network. So whether that device is officially a router or a gateway doesn't really matter to us as users, as long as we can get to other networks, and most notably among them, the internet. Finally, access points, at least these days, most commonly refer to Wi-Fi extenders, used to boost the range of signal coverage. Now, some of you might have these devices at home, particularly if your home is large or there are several floors between you and the primary router, but a very common example of their use is in airports and hotels, where the coverage area required is far beyond what a single Wi-Fi router can handle. But in those cases, it's all still the same network. So a good way to think of access points is as wireless switches. Just like in a wired network, you can plug your computer into any available wall port, you can connect your mobile device to any available access point, and you'll have full access to the network. Now, the access points themselves are often connected to the primary router using wired connections, but they accept wireless connections from our local devices, providing the ability to cover a much larger distance. If you're using one at home, then it might still use a wireless connection back to the primary router, but in this case you can think of it as more of a repeater or a signal booster. As long as the access point is within range of the primary router, then it can boost the signal to extend that range. But in either case, access points really don't provide any functionality beyond range extension, so you still need the primary router for internet access. But given these types of devices, in the right combination, they're able to provide us with the connectivity we need in just about any situation. In this presentation, we'll examine the role and features of firewalls, which are commonly implemented as either applications or physical devices that effectively sit between the internet and internal networks to provide monitoring and filtering of packets to help increase the security of your environment. In short, the firewall's primary job is to examine traffic so that acceptable or desirable traffic is allowed to pass, while suspicious or potentially threatening traffic is not. Now, the term firewall itself is somewhat generic in that there are several types of firewall, including but not limited to software, packet and/or application layer, stateful inspection, proxy server, and next generation. Now, a software firewall is exactly that. It's installed as an application that can run on a computer, but they're typically meant to protect only that computer. In other words, these would not provide any kind of network level protection. There are many different software firewalls available from many different vendors, but each instance only protects the computer on which they're installed. Packet layer and/or application layer refers to the layer of the OSI model at which traffic is examined. Packet layer firewalls work at the transport layer, where the primary protocols are TCP and UDP. The application layer is the highest layer at which there are many protocols, but common examples include HTTP for websites and SMTP for email. In both cases, though, the firewall is looking for packets that might contain malicious or suspicious data, or anything that might not match the protocol's normal implementation, and if found, those packets are blocked. Stateful inspection refers to the connection itself between the communicating systems, which is actively monitored by the firewall for the duration of the transmission to determine which packets to allow and which to block. It doesn't generally monitor at a specific level or look for particular protocols. Rather, it monitors the entire conversation, so to speak. A proxy server generally acts in both directions in that all outgoing and incoming traffic must pass through the proxy, and it typically filters based on a predefined set of rules. For example, in the outgoing direction, the proxy can check the requested URL to ensure that people at work aren't able to access questionable sites, and incoming traffic can be similarly blocked based on the originating URL or the type of traffic or protocol being used. And next-gen firewalls typically refer to the deepest level of inspection, whereby it isn't just characteristics or attributes of the packets that are examined, rather the entire packet, contents and all, can be examined for detailed security analysis. Another basic characteristic of a firewall is known as host-based versus network-based, which to a degree comes back to the software firewall just mentioned. But there can be more to it than just the fact that it's software. However, a host-based firewall simply means that it is being implemented on just that host computer. So in virtually every case, a host-based firewall is going to be a software implementation. However, a network-based firewall is designed to protect the entire network. So its most common implementation is a hardware device that sits at the perimeter of your network, in essence between your local area network and the internet. But it doesn't have to be a physical device. In other words, you could have a software-based firewall on a standard computer, but it could be configured to act as a network-based firewall. So what it comes down to is that software firewalls could be either host-based or network-based, but hardware firewalls are almost always network-based. Which one you choose to implement is entirely your call, but for the highest level of security, you could implement both, so that if something malicious does happen to get through the network firewall, your host-based firewall is still there as an extra layer of defense. Plus, network-based firewalls do not monitor traffic on the internal LAN. So, with a network-based firewall only, there would be nothing to prevent a malicious internal user from compromising other internal systems. Primary features of modern firewalls include malware blocking, application attack blocking, and intrusion detection and prevention. Now, it's important to note that these and several other considerations that we'll see in just a moment are not always default features of every type of firewall. At their core, firewalls are designed to examine traffic and make a decision as to whether that traffic should be allowed or blocked, but the specific features and the types of threats that can be blocked will depend on the type of firewall. On that note, other key considerations are the firewall's ability to examine traffic at multiple layers of the OSI model, its ability to provide network address translation, which permits internal private IP addresses to communicate on the publicly addressed internet, any antivirus capabilities that might also be available, and in this regard, I should point out that antivirus capabilities are often not present by default. That's usually handled by separate applications, but again, it's a feature that is certainly available in some cases. But you should verify if that's the case for the firewall you're considering. Its ability to block spam email messages, denial of service attacks, backdoor malware, remote access threats, and malicious macros. Now, all of that said, many firewalls may be able to detect and block all of these threats, but it would depend on its configuration. So proper and thorough firewall configuration often needs to be left to advanced network security personnel, at least when dealing with network-based firewalls. But if you're just considering a software-based firewall for your home computer, then most of these would either have a default configuration or they would have an initial setup wizard which would prompt you with various questions as to your normal internet activity, and an appropriate configuration would then be implemented automatically based on your responses. Then, if a questionable packet arrives that the firewall is uncertain about, it will likely prompt you to ask if this traffic is recognized or not, and based on your response, a new rule could be created. Ultimately, if you want to increase the security of your home computer or your network, a firewall of some type should be implemented, but I should also point out that many devices and operating systems have firewalls by default. For example, all computers running current versions of Windows do have the Windows Defender firewall in place by default. In a default configuration that is generally secure, so you don't need to do anything as a user to simply make use of it. But as mentioned, more advanced configurations should generally be left to security professionals. In this presentation, we'll provide an overview of the various 802.11 wireless protocols that are in use and the features of each one. Now, just quickly, the reason you see 802.11 in reference to wireless technologies goes all the way back to February, or the second month, of 1980, hence 802. And the 11 refers to a series of specifications that were defined by various entities to determine different ways by which devices could network with each other in a standardized manner. And 12 primary specifications were defined, such as Ethernet, token ring, and fiber optic. And 11 covered wireless networking methods. Hence, the names of the protocols currently in use still refer to those specifications to this day. But of course, all technologies develop and improve over time, So, the 802.11 family of protocols defines several modern wireless networking standards to facilitate the ability for computing devices to connect to and communicate over wireless networks. Now, there are several characteristics of each protocol that distinguish them from the others, but one of the most common is the transmission frequency used and the channels that are supported within that frequency. Now, it might seem at first glance that frequency and channel refer to the same thing, but not quite. For starters, there are two primary frequencies in use with current wireless protocols, 2.4 gigahertz and 5 gigahertz. And this brings up an immediate consideration in terms of compatibility. In order for any two devices to communicate wirelessly, they must be using the same frequency. So if your wireless router is using the 5 gigahertz band, all connecting devices must also use 5 gigahertz and the same channel. So how do channels relate to the frequency? Well, the two bands used don't refer to exactly those frequencies. They're more of a generalized value, whereby the frequency referenced actually covers a range of frequencies, with that range divided up into more specific channels. So in the 2.4 gigahertz band, for example, channel 1 actually begins at 2.401 gigahertz and ends at 2.423. Channel 2 begins at 2.406 and ends at 2.428. Channel 3 begins at 2.411 and ends at 2.433. And this continues all the way through 11 channels. Each channel covers a range of 20 megahertz, and each channel begins 5 megahertz away from its predecessor. Now, you might notice that this results in channels that actually overlap with each other, which can result in some interference if there are devices close to each other that are using neighboring channels. But if you follow that sequence along, channels 1, 6, and 11 are far enough apart from each other that they don't overlap. So they're often suggested as the best options to use if you are experiencing interference. And that interference might not have been from something like a neighbor's wireless router. Many other devices, such as cordless phones and baby monitors, also use the 2.4 gigahertz band. Now, the 5 gigahertz band is also divided up into channels, but there are varying channel widths and many more channels overall. Plus, fewer devices use this band. So, which one is better? Well, the use of the 5 gigahertz band is more recent, so there is generally less interference, and it does support faster speeds, which of course is what we all want, but it's not quite that simple. Higher range frequencies can carry more data, hence the faster speed, but lower range frequencies are able to travel farther and can penetrate obstacles such as walls and floors more easily. Plus, if your environment still has some older devices in use, they may not support the 5 gigahertz band at all. So, like most things, it will depend on the situation. But in general, if you want speed, then certainly go with 5 gigahertz. But if you need better range with legacy support, then go with 2.4 gigahertz. So, as far as the protocols themselves, they're distinguishable from each other by the use of letters after the 802.11, with the exception of the very first protocol that was introduced, which was simply referred to as 802.11. Which these days will often be referred to as legacy because as of the time of this recording, it's over 25 years old and would almost certainly not be in use in any current environments. But it used the 2.4 gigahertz band and supported speeds of only 1 to 2 megabits per second. 802.11b then was released fairly shortly after the original, and it was really the first version that was widely adopted in homes and offices. It still used the 2.4 gigahertz band, but supported speeds of up to 11 megabits per second. Interestingly enough, 802.11a was released after B, and quite honestly, I'll tell you that I'm really not certain as to how the designating letters were chosen, because the next release after A was G. Now, A was the first version to use the 5 gigahertz band, and it also introduced a significant jump in speed up to 54 megabits per second. But recall that the frequencies used are not compatible with each other. So for everyone who just recently went out and spent a significant amount of money to implement a version B router and possibly several wireless adapters for their computers, they weren't very likely to just immediately turn around and buy everything all over again. And I should also mention, for the benefit of our younger viewers, that in these days, the internet service coming into your home did not include Wi-Fi. We had to go out and purchase our own Wi-Fi routers, and devices such as laptops did not come with Wi-Fi adapters built in. And mobile phones such as iPhones and Androids didn't even exist yet. So where all of that is standard today, back in the earlier days of Wi-Fi, it was a much more expensive undertaking to implement a full wireless network in your home or office. So version G was introduced after A to match its speed of 54 megabits per second, but it used the 2.4 gigahertz band, making it compatible with B. Although if your new G router was being used with a B device, you would still only get 11 megabits per second for that device, but they would still work. So as you purchased newer devices that supported G, they would be faster and you still had backward compatibility. 802.11n introduced the use of multiple antenna to increase data rates up to 600 megabits per second, and due to the growing use of the 5 gigahertz band, but with consideration for backward compatibility, it introduced the ability to transmit using either the 2.4 or the 5 gigahertz band, but it could only use one or the other. 802.11ac followed, at which point we also start to commonly see the use of more user-friendly version numbers as opposed to the somewhat cryptic letters. So the term Wi-Fi 5 is synonymous with 11ac, and it introduced the ability to use both transmission bands at the same time. So there are quite literally two separate transmitters and receivers in these units that can operate independently and simultaneously. And of course, it increased the speed again up to 1.3 gigabits per second. And finally, as of the time of this recording, the most recent version is AX, also known as Wi-Fi 6, which also supports both bands simultaneously and offers a theoretical maximum speed of approximately 10 gigabits per second, although there aren't a lot of devices currently available that support that kind of speed. So, as it stands, these days, Wi-Fi 5 or 6 are likely being used in most environments due to both their speed and their support for both bands. And most of the time, all we have to do as users is to provide the necessary password to join our devices to the network. But it's always a good idea to verify the attributes of any wireless networking device before making a purchase. In this video, we'll provide an overview of some considerations for achieving the highest quality wireless signal strength possible, along with the factors that can interfere with that quality. Now, to begin, one of the most important considerations with respect to quality is what's known as the signal-to-noise ratio, which refers to the level of other radio frequencies that are being picked up by your device in addition to the desired signal. In short, in an ideal situation, there would only be the wireless signal you want and nothing else, which would result in a virtually perfect signal-to-noise ratio of 100% signal to 0% noise. But of course, that just doesn't happen in the real world. Other radio frequencies nearby can all produce signals that are just noise as far as your Wi-Fi connection is concerned. Now, the unit of measure to indicate signal strength is the dBm, which stands for decibels per milliwatt. And an ideal signal strength range is from -30 to -90 dBms. And it's important to note that those values are expressed as negatives because -30 is a higher signal strength than -90. But what you're looking for is the biggest gap possible between signal strength and noise. So coming back to my perfect world example of zero noise, well, that would be the biggest gap you could possibly get. Conversely, if there was as much noise as signal, then there's no gap at all. Now, how do you even know what kind of values you're experiencing? Well, there are software applications that you can download and install on your computer that can analyze all signals being received and provide you with these values. As for some of the more common sources of interference, they include a neighbor's Wi-Fi device, microwave ovens, nearby radar stations, or cordless phones. But it's important to note that most of these are all transmitting in the 2.4 gigahertz band as opposed to the 5 gigahertz band. Now, I'll come back to that in just a moment. But with respect to getting the most out of your signal strength, it's a good idea to obtain a signal analyzing software package and attempt to inventory and or identify the devices in your area that are causing interference, which might require a bit of surveying, so to speak, in that in order to get the best overall picture of the signals in your area, you literally need to walk around with your device in hand to see how the signal strength varies from place to place. And of course, you also need to consider the location of your primary access point in relation to the devices that are connecting to it. And the more walls and or physical barriers there are between them, the lower the signal strength will be. So again, in a perfect world, the access point would be right in the center of all devices that connect to it, with no barriers between them at all. But in practical terms, it usually just means attempting to find a location for the access point that isn't buried away in something like a utility room that might have concrete walls. With a better idea of the signal quality in your area, you can then possibly reconfigure it for better performance, which might involve changing the frequency, which again I'll come back to, and or possibly using an access point that supports what's known as beamforming, whereby the access point itself includes signal analyzing software and can actively refocus signals to steer them around areas of interference as they're detected. So coming back to the settings and transmission band, one possible solution might be to simply change the transmission frequency from the 2.4 gigahertz band to the 5 gigahertz band. And this is because, as mentioned earlier, there are many more devices that use the 2.4 band as opposed to the 5. So that change alone might result in a significant increase in performance, but it's not quite that cut and dry. For starters, all client devices must support the 5 gigahertz band, which is quite likely these days, but some older devices might only support the 2.4 band. And while the 5 gigahertz band is less susceptible to interference, it typically doesn't penetrate walls and obstacles as well as the 2.4 band. So if you have a lot of barriers to deal with, then changing to the 5 gigahertz band might not result in any improvement at all, and in fact it might even be worse. Another option related to the band is the channel, because each band does not use the exact frequency indicated by their name. Rather, it's a range of frequencies that are divided up into smaller channels. So if, for example, your signal quality is poor because of a neighbor's device being very close by, simply changing the channel on your device might solve the problem. Another option is to increase the range of your own access point by implementing a repeater and or a range extender, which can act as a relay, so to speak, so that if your device is slightly beyond the range of a good quality signal, then the extender can quite literally increase the range. They can connect to your primary access point either wired or wirelessly, but as long as they have a good connection to the access point, they can boost the signal they receive and retransmit it so that your device receives a stronger signal. Now, to finish up, with respect to all of this, it would generally fall under the category of only needing to address it if and or when it becomes a problem. In other words, if you have just implemented a new Wi-Fi device at home or even in an office, and all client devices seem to be able to connect without issue and they experience good performance, then spending a lot of time and effort to analyze the signal-to-noise ratio might just be creating more work. But if users are complaining that they can never get a reliable connection, then you should certainly investigate further. For our final presentation of this course, we'll examine several methods and best practices to get the most out of your Wi-Fi performance, beginning with finding the ideal location for the router, which should generally be in an area that is as open as possible and as central as possible. For example, at home, If you have a multi-level house and your client devices are most commonly used on the third level, then you should avoid installing the router in the basement. The router should also be placed as far away as possible from other potential sources of interference, particularly in an office environment. You should try to ensure that your access point is not immediately adjacent to the access point of another tenant or installed in a utility closet right next to the central power panel for the building. If interference is an issue, then try changing the channel on both the access point and the connecting devices, and optionally consider replacing the default omnidirectional antennae of the unit with high gain antennae that support a more focused signal. Most access points do have removable antennae for that very purpose. Interference can be reduced by changing the transmission band of the access point from 2.4 GHz to 5 GHz, as there are more general household devices that use the 2.4 transmission band, such as baby monitors and cordless phones. Alternatively, just be mindful of the band that is used when considering the purchase of any new device that does transmit wirelessly, and try to find something that uses a band other than that of your Wi-Fi. If your devices seem to be right on the border of good quality signal, consider adding a repeater and/or an extender, which can help to increase the range of your Wi-Fi, and also try to upgrade your device to the latest standard possible to ensure that the speed you're getting is as fast as possible, particularly if you've had the same access point for many years now. You might also need to consider the wireless adapter itself on some devices. Now, more specifically, this would only be applicable to systems such as desktop computers that normally don't have built-in Wi-Fi adapters, because it's unlikely that you'd be able to change the built-in adapter of something like a laptop or a smartphone. But in the case of a desktop, you can buy internal expansion cards that do have antenna, but if the computer is tucked away under a metal desk, then it would likely be a better option to install an external adapter that connects using a standard USB cable that would allow you to place the adapter in a more open area. And for all Wi-Fi adapters, be sure to regularly update the software and drivers to ensure that any bugs are addressed. As for security, you might consider changing the Service Set Identifier, or SSID, which in simpler terms is just the name of the network as seen by your receiving devices. For example, at home, if your network name references your own name or address, others within range will see it and know that it's your network. So it's generally better to make the name a little more anonymous, and you should also be sure to change the password to something that is more secure than the default. Now, that's going to be dependent on the make and model of your access point and/or the provider, but just as an example, a local provider in my area used to set the default password to the first initial of your name plus your phone number. So anyone who knew you and knew that you were using that provider would know your password if you didn't change it. Now, I should also mention that they stopped this practice, but in short, your password should only be known to you, and it should be something that is complex and not easy to guess. When using public Wi-Fi connections, while they're certainly convenient, try to avoid any kind of open connection because it would not have any encryption. They're identified by the fact that there is no password required to join, and if you do have to use one, try to avoid any sensitive activities such as online banking or making purchases, and ensure that your local firewall application is configured for a public network, which means it will typically reconfigure itself to assume the highest level of threat protection. You should also verify that the network itself isn't a malicious network. For example, you might go to a coffee shop and seemingly connect to their network because it has the same name as the shop itself, when in fact, that shop doesn't even offer Wi-Fi at all, and the network has been set up by a malicious user who happens to live very close by. So you can just verify with the shop that the network is theirs. And be mindful that on a public Wi-Fi, anyone can connect, even if their devices have already been compromised through virus infection or other malware. So again, try to limit the use of public Wi-Fi networks as much as possible. Finally, ensure that your device is using the most recent security and encryption methods. Among those commonly used are Wired Equivalency Privacy, or WEP, Wi-Fi Protected Access, or WPA, and WPA version 2. As you might expect, WPA2 supports higher security than WPA, and both of them provide better security than WEP. Now, in fact, WEP is only mentioned here because it was one of the first wireless security protocols, but it is not considered to be secure by today's standards. So the only reason why you might implement it is if you're still supporting very old devices. In other words, it might be needed for backward compatibility, but I would say that WEP was abandoned as a secure protocol by the early 2000s, so it would be unlikely that you would see it in use today. WPA is certainly preferable to WEP, but its successor, version 2, introduced support for stronger encryption, so it's the current standard for today's implementations. But again, original WPA might still be needed for a certain degree of backward compatibility, but whenever possible, use WPA2. In short, wireless technologies are continually improving and being upgraded, so by implementing these and other best practices, you can help to ensure that you're getting the most out of those improvements. So in this course, we've examined basic concepts surrounding computer networking and wireless technologies. We did this by exploring the Internet Protocol Suite, TCP/IP, network packets and DNS, LANs and WANs, IP addresses, IP version 4 versus IP version 6 and MAC addresses, HTTP and HTTPS, POP3, SMTP and IMAP protocols, networking device types, firewalls and wireless protocols, and Wi-Fi quality and best practices. In our next course, we'll move on to explore basic concepts surrounding computer operating systems.